Hello, today we are going to start a new topic called as Properties of Fourier Transform. We have started a new unit called as Integral Transform. So till now we have covered it topics like integral transform, the definition of integral transforms, examples of the integral transforms. Then we have completed one theorem called as Fourier Integral Theorem. This is a statement. It's a 4-step proof which we have done. Then we have done one more theorem, that is Fourier's complex integral, which is a 2-step proof. Then we have done just a substitution for Fourier transform, which is the most important topic which is required for our further problem solving as well as for the further proofs. So just have a look at the definition of Fourier transform. Capital F of s is equals to 1 upon square root of 2 pi integral minus infinity to infinity f of t e raised to ist dt. Just see, and the f of x is equals to 1 upon square root of 2 pi integral minus infinity to infinity capital F of s e raised to minus of is x ds. So this we are going to use in our today's topic, that is properties of Fourier transform. We have done one more theorem called as Convolution Theorem. Then we have done the Fourier transform of its derivatives. So this was our first, second, third, fourth, fifth, 5 derivatives we have done. Then later on we have given a proof for the relationship between the Fourier and the Laplace transform. Then we are going to start with our proofs. Okay, so these topics I'll explain you later. Let me first complete the proof or the properties of Fourier transform, and then I'll get back to these topics. Okay, so let's start this. So today's topic is properties of Fourier transform. So we are starting our first property, that is linear property. So let us give the statement for this. If f1, capital F1 of s and capital F2 of s, these are Fourier transforms of f1x and f2x respectively, then we need to prove something. So what is that proof? Capital F in the bracket a f1 of x plus b f2 of x which is equals to a capital F1 of s plus b capital F2 of s. Okay, and in this part the a and b are constants. Okay, so let's start our proof. Okay, we know that what we know, f1 s, this is a Fourier transform, so which is equals to 1 upon square root of 2 pi integral minus infinity to infinity e raised to isx f1 of x dx. I hope you remember this formula from where we have written this. Backside I told you f2 of s is equals to 1 upon square root of 2 pi integral minus infinity to infinity e raised to isx f2 of x dx. Okay, so now what I'll do, I'll add both these. So after adding, what I'll get, I'm not marking this as equation number 1 and 2, simply I'll add. So linear property, it is also called as addition property. So f in the bracket a f1 x plus b f2 of x. What I'll get it as, which is equals to 1 upon square root of 2 pi integral minus infinity to infinity e I s x. Both will have e I s x, and in the bracket a f1 of x plus b f2 of x, b f2 of x f2 of x and dx. Okay, so next page, that was page number 12. So this is page number 13. Okay, so dx. So this next step, it will be like a 1 upon square root of 2 pi integral. So what I'll do, I'll separate both these terms. I have written it together. Now what I'll do, I'll separate both these terms. This term, yeah, forgot only. I just the closing this. So integral minus infinity to infinity e raised to I s x f1 of x dx plus b integral minus infinity to infinity 1 upon square root of 2 pi e raised to I s x f2 of x dx. Or in general, you can write it this as a f1 of s plus b f2 of s. I hope we have completed our proof. That is a f1 of s plus b f2 of s. Hence, proved. We are done with our linear property. Now next property, which is the next property? Next property is change of scale property. Change of scale property. Now if f of s is the complex Fourier transform of fx, then f of ax is equals to 1 upon a f of s by a. Okay, so this is equals to this, we have to prove. So how we will proceed? Proof. As we know that, what we know, that f of s is equals to 1 upon square root of 2 pi integral minus infinity to infinity e raised to I s x f of x into dx. So I'll take this LHS. So f of a of x. Okay, so what I'm getting is 1 upon square root of 2 pi integral minus infinity to infinity e raised to I s x f of, instead of x, what I'll write it as ax dx. Okay, now what I will do after this step, what I'll do, I'll put the values of this ax as t, and my dx will be dt by a. So substituting this value in this equation, so 1 upon square root of 2 pi integral minus infinity to infinity e raised to I s. This x will be t by a. A will go to denominator, so I have not written this step. T by a. F of ax will be f of t, and this will be dt by a. I'll take out this a as common outside. So what I will get it as is 1 upon a into 1 upon square root of 2 pi integral minus infinity to infinity e raised to I s t by a f of t into dt. So this whole term is what? It is f of s by a. Okay, so which is equals to 1 upon a. This is constant, this will be there, and this will be f of s. S will be there, and this is divided by t, so it will be f of s by t. S by t. So as we have to prove 1 upon a is equals to 1 upon a f of s by a. So hence we have proved this. So which property is this? This is our second property. What is the second property? Change of scale property. Okay, so now our next property is shifting property. Next property is shifting property. Third property, it's a shifting property. If f of s is the complex Fourier, if f of x is a complex Fourier transform of small f of x, then what happens? Capital F of small f of x minus a is equals to EISA into f of s. So what we have to prove is this is equals to this. So first step, we know that. What we know that? That is f of s is equals to 1 upon square root of 2 pi integral minus infinity to infinity e raised to I sx f of x dx. Now what I'll do? I'll take the LHS. So f of x minus a, which is equals to 1 upon square root of 2 pi integral e raised to I sx f of x minus a into dx. Again same thing like previous one, but here in this case what I will do, put x minus a is equals to t, so that dx is equals to dt. Okay, so what will happen? 1 upon square root of 2 pi integral minus infinity to infinity e raised to I s. So x is there, so x will